Hi, everyone. Welcome to BIO347 by Statistics. This is lecture 2, part 2, and we're going to talk about hypotheses primarily in the Nyman-Pearson Null Hypothesis testing framework. All right, and I'm going to go over these items that you see on the left: null hypotheses, alternative hypotheses, etc. All right, a null hypothesis. So a null hypothesis, which we can also write H naught, okay, is one of no effect, right? It can literally mean like no effect size, okay? Or it can mean as expected, okay? And I'll give you an example where we can test something as expected, and it will not mean there's no effect, but things occurred as we expected. So in a dihybrid cross, when you cross, if you remember this, you should get, when you cross two traits, right, and are heterozygous for both, you get a ratio of 9 to 3 to 3 to 1. So when you do a dihybrid cross of Mendel's peas, you had green smooth, green wrinkled, yellow smooth, yellow wrinkled in these ratios. The null hypothesis is that you'll get 9/16, 3/16, 3/16, and 1/16 of those ratios. So if you end up failing to reject the null, it means you have those results, right? So the null hypothesis, and this is out of 16. So if you add this up, you get 16. So 9/16, 3/16. So these are the ratios. If this was just, you had no idea and there was no effect, then you might expect something that might be, instead of 9 to 3 to 3 to 1, would be 1 to 1 to 1 to 1, okay? Where you get an equal number of all these. So it's important to understand what your null hypothesis is. It's just, you have no idea what's going on, or do you expect things to turn out as expected, okay? So it's important that you understand what you're testing, okay? All right, so let's get rid of this. So null is one of no effect. So the alternative to that is that you do have an effect. And it's important to understand, let's do directional versus non-directional. And these are also called one-tailed. And these tests are called non-directional, are called two-tailed. Okay. So directional means you think you know what's going to happen, okay? Non-directional means you have no idea, okay? So this is something that I'll call ignorance, and that's not a bad thing. In fact, when a scientific field is young, you can expect that you'll have a lot of non-directional hypotheses. You just know something is happening. So I'll give you an example of a directional. So you have your cornfield, right? So you have two fields, and you have a control field, and you have plus fertilizer, right? You expect despite variation in corn plants, you expect on average that the fertilizer will be taller than the controls. Okay, that is one tail, that is directional. This implies the direction. Okay, two-tailed would mean you have a control and you have chemical X, and you don't have any idea if chemical X is good for corn or bad for corn. So here's your control. You just don't know. Okay, what you say is it's just not going to be the same. Okay, it could be smaller or taller than the controls. Okay, so we could imagine if this was a herbicide, right, like a weak herbicide, you would actually have it like this. But this implies you know something about your system, and this implies you have no idea what's going on. Okay. All right. What about the tails? What does that mean? So the tail, if you remember the previous lecture, if we look at the distribution of our corn plants, so we have our control, and we can say plus fertilizer. Okay, and when we talk about tails, we're talking about this tail. Just remember, this is essentially if the null were true, right? If fertilizer did not have an effect, it'd be the same as control. So the tail we're interested in is this overlap here. Okay, so that's the tail. Non-directional, right? What you're interested, you have your control, and then you have this. So the question is it this one or is it this one? In which case you can look at this tail or you can look at this tail. So you're looking at two tails of the control, okay, is what you're testing, right? So one tail implies you know the direction, and in this one, you don't know the direction, right? Chemical X could make things smaller, could make things taller, okay? Here's the thing. If you remember, what we said is this area is going to be 0.05. So if the area is smaller, so we have something less than, right, equal to or less than 0.05, we're going to reject our null hypothesis. Okay. So you have a 5% chance of making a mistake here. If we were to make this 0.05 and 0.05 for the whole experiment, right, we have 2 times 0.05, right? So we basically doubled our chances of making the error of rejecting the null. So usually what we do in a two-tailed test, we say we're going to use a p for significance of 0.25, right? So what that means is we're going to use a smaller area here and a smaller area over here, okay? And together that's 0.05, okay? So it's important to know whether you're testing a one-tailed test or a two-tailed test. If you know what's going on, it's a one-tailed test. If you have no idea what's going on, it's a two-tailed test. All right. So this was for testing the means, right? So we want to know if these means are different, right? So this mean and this mean. We can look at trends. So let's compare these things when they're trends. Okay, so if we're looking at a trend, our null is here. If we have, let's choose a different color. If we have a directional, we say like, as we increase temperature of the aquarium, our amphibians can swim faster, okay? If we have no idea, and we have a type 2, it's going to look like this, right? And then we're dealing with slopes. When you have a question of slopes, we call our slopes betas. So let's use beta. So here, beta naught. Let's say this beta A is greater than beta naught. Okay, and this beta, let's call it beta B, right? And all we know is beta B, our slope, right? These two slopes is not equal to, okay, beta naught, which is equal to 0, right? So we can say beta B is not equal to 0. Okay, that's how we do this. Let's look at the corn plants again, but let's not look at it with the frequency distributions, but we'll look at it with box plots. Okay. And if we look at this, and we're really interested in the means, and in the mean, we can represent with a mu. Okay, so mu, the control, okay, is less than mu of the fertilizer group. If we have chemical X, right, we can have taller corn and we can have shorter corn. We just don't know, and what we can say is it's just not the same, right? So these are the ways of expressing our hypotheses. So alternative hypotheses, if one-tailed, means we have some sort of direction. If it's two-tailed, it means we don't know, and you use a not equal sign. All you know is it's just not the same. That's our alternative. All right. Very good. All right. Power. Okay, what is statistical power? It's the ability to reject false null. Right. So this is kind of a weird concept, and we'll get into examples why. So, for example, let's look at some trend. Here's the null. Try and draw a straight line as best I can. Here is the alternative. Okay, so we're going to say beta, actually let's call it beta null. This is beta alternative. Power is our ability to detect that this slope is real or not, right? So this is a purely statistical test, okay? Because if you don't have, if this is actually the graph, and you don't find a significant difference between your alternative and the null slope, right? That does not mean that this isn't real. You may be able to detect it, but that doesn't mean this has biological significance as well. Just something to think about. All right. So, how do we increase power, right? So what we want to do is reject false null, right? Let's talk about the three things that go into sample size. So that means getting a P that's small enough that you reject the null if it indeed is false. Things you can do. Increase sample size. We can reduce variability. Okay. How do you reduce variability? So if you're doing a test on, say, mice, right? There's all kinds of strains of mice. You wouldn't have a mixed bag of mice. You would have a particular strain and just use the strain. You wouldn't say, we're going to use a highly variable system. That reduces variability, but it also reduces your inference. Just something to keep in mind, okay? So with your corn, for example, you want to reduce the genotypes, right? So you test one genotype with fertilizer without the other fertilizer. If you have the same genotype and you have the same soils, you should get corn plants that are very, very similar in height. All right. Or you can increase the effect size. Okay. So these are the three basic ways to increase your power. How do you increase the effect size? Usually, think about this. If you're looking at a trend and here's your null and here's your slope, right? Effect size, think about this. If this is temperature, okay? If you were to compare this versus this, you don't have much effect. But if you were to compare this versus out here, right? So by increasing the range in X, you can detect or get this bigger difference out here, right? So if you detect a narrow range, you're not going to see a big difference along that line. You increase it, you're more likely to find something going on. All right. Likewise, if you had two groups, right? You can have a control group, which gets 0 milligrams of some drug. You could do, if you tested, 10 milligrams, you may not find as large an effect as if you had 100 milligrams of a drug. Okay. And there's right ways to do this and wrong ways to do this. All right. Reporting. So reporting has to do with when you write up your results, okay, and you want to write a paper or you have a report or somebody just wants to hear you, right? Reporting. Right? You state what your alpha is. So we usually say we tested with an alpha of 0.05. When you get your results, you report your test statistic, your degrees of freedom, and your p-value. And oftentimes they'll go right together. So you would say chi-square, degrees of freedom equal 4, p equals 0.02. Okay, and you would put that after you say you reject the null. You would put it just like chi-square equals whatever. Okay, now don't just write a chi-square, but you would write chi-square equals, 12.92 or something, whatever your chi-square ends up being. All right, and then for effect size, there's a delta, and technically that's your effect size. I don't think I've ever seen effect sizes expressed like that. I've seen it in textbooks, but I've never seen effect sizes expressed like this. What most people like to see is things like percent. So if you're testing control versus a fertilizer, you would express the increase in the percent, okay? Or a slope. But you put it in meaningful terms. And what I mean by that is you say for every step you take here, so for every degree of increase in this, right, your increase or decrease occurs on this line. So for every unit of temperature, for every degree, every 10 degrees increase in temperature, your swim speed doubles, for example. So that would be good reporting of effect sizes. So if you remember what goes into a p-value, right? Degrees of freedom, that's here. Effect size, and that would be this, or it's implied in the slope. And what about variance? Okay, the third thing that goes into. So oftentimes what you can say is you can report standard errors. Okay, and we'll get into this later. Or just by showing a graph. Okay. There's ways, when you look at this graph, you understand from the points along the line, right, your fit line, that the variance is either high or low, right? And we'll get into more technical ways of reporting all these things. All right. I do want to erase. All right. Problems. So it's called type 1, which is, oops, I'm not sure what I'm spelling there. Rejecting a true null. Right? We should not reject a true null. So it's falsely rejecting a true null. That's a type 1 error. Okay. Type 2 error. Let's fix that. type 2 error is failing to reject a false null. Okay, so this is false positive. Right, and this is a false negative. Right, and the way this works is you can express this in a grid. Okay, and you have HO, whether it's true or false, and then rejected based on your test statistic are not rejected. Okay, so false positive, right? So you reject an HO that's true. So this would be your type 1 error, and then a false negative. This would be your type, type 2 error. Okay, so hopefully you do not reject a null that's true, and you reject a null that's false. Okay, and a lot of this has to do with power as well. All right, so let's talk about p-hacking. What is p-hacking? P-hacking means there's ethical and unethical ways to p-hack. Remember that if you get significant results, you're more likely to publish them. If you're dealing with a drug, it means your drug works, right? Statistically, doesn't mean biologically, either way, right? So p-hacking. What does it mean? It means you increase your sample size after initial experiment. We can say fails to reject. So you repeat it with a larger sample size. That is unethical. Okay. If you report it, slightly better. Okay. So if you do it and you don't say, you know, we ran our test with 50 mice and our P was 0.06. So we ran it with 20 more mice and we rejected the null at this point. If you do that, that's ethical. You should have ran your experiment with as many mice as you could have to begin with. But if you don't say it, if you say, we ran our experiment with 70 mice and got a significant result, that's unethical p-hacking because you didn't tell the reader that you got a non-significant result with a smaller sample size. So the same thing goes with increasing effect size. So let's say you give your mice 20 milligrams of a drug and it doesn't work, and you bump it up to 25, test it works, right? You should say non-significant results, repeated it with a higher amount, and got significant results. That's fine. I think you can do almost anything as long as if you're reporting the results, it's much more ethical than doing something and only recording the end part, leaving out the stuff you did beforehand. That's not ethical. So increasing sample size and effect size, right? That's the way to p-hack. And then 2 is large number of tests, right? So if you do a large number of tests, if you do a test, the probability in any test is getting 0.05. If you falsely rejecting a true null hypothesis. And if you do another test, right, now your chances are 0.05. You keep doing that, your chances are 0.05, 0.05. If you flip a penny 50 times and you do that 20 times, on average, you should find a penny where you reject the null hypothesis of a fair penny, where you actually have a fair penny, but the probability was low, so you reject it, right? If you do a large number of tests, one of those tests, just by chance, will give you statistically significant result, right? Where it didn't actually mean anything. It was just the way that you drew your samples. And I would say this is unethical because if you don't adjust for the number of tests, you're either doing it out of ignorance or you're doing it out of malice. And either one is no bueno, okay? So you do a large number of tests, you have to adjust for it. If you don't and only report it's really bad. I would say it's just malice. If you do, say, 20 comparisons and you only report the statistical significant ones, right? That it's a mustache, not a bow tie. But we can add a bow tie. Right. So if you do a whole bunch of comparisons and you don't tell anybody, that's malice. So that's bad. That's unethical. And I don't know how you would catch it. You want to catch it in a paper. The reviewers want to catch it, but if that's what's found out to be true, you should lose your funding. So that makes me really sad, right? As if you were somebody that dropped their ice cream and it started to melt. Okay. All right. So that's ends part 2. And I think one more. Yeah, we have Bayes to talk about, but that's the end of part 2.